Hey, in this video we'll see a little bit about the expected value of a random variable. So, namely, we will see the following lemma. So we assume we have an integrable random variable, and well, this means the expectation of the modulus of y is finite, and furthermore we assume that y is at least 0 almost surely, which means that we wouldn't have needed the modulus here. So the statement now is that the expectation of y is the integral from 0 to infinity, and then we look at the tail of the distribution and we take the Lebesgue integral. And now let's prove this. So we do this in the standard way. We start with characteristic functions. So we take a measurable set, and now we look at the expectation of the characteristic function of the set, which is just the probability of this set. Now we look at the integral here. 1a is bigger than t, and for t bigger than 1, this probability is certainly 0. So we can just take the integral from 0 to 1. And now we see for t in the open interval from 0 to 1, we get that this is just that the probability that 1a is bigger than 0, which is nothing else than p of a, and we integrate over the unit interval, so this whole thing is also the probability of a. So we've shown it for characteristic functions. So maybe let's say a first step. Then there's the second step. We show it for functions of the type I equals 1 to n alpha I, and then some characteristics functions, and now we assume that the alpha I are non-negative and also AI pairwise disjoint. We don't have to assume that the AI are pairwise disjoint, but if we modify the alpha I here and possibly the finitely many sets AI here, we can assume that this function is of this form after modifying. Okay, and now we again look at the expectation of this. So we know that it's linear, so we get the sum and then alpha I and then p of ai. And now we look at the integral. So integral from 0 to infinity. Let's look again at what we have to consider. So we need the probability that our random variable is bigger than t, and our random variable is the sum from 1 to n alpha I and then the characteristic functions, and this should be bigger than t. Well, and now we've assumed that the AI are pairwise disjoint. So in order for the sum to be bigger than t, we need that one of these AIs are one of these characteristic functions is not 0, and also of course that the alpha I is bigger than t. So let me write it out. What we have the union from 1 to n, and then of the sets where let me write it. Alpha I and then the characteristic function of AI is bigger than t. And this union is disjoint, as we've noted several times already. So now we get the sum equals 1 to n, and then of the probability that this set where alpha I and then the characteristic function is bigger than t. Okay, we also can take the sum out, but that's not the important part. Now let's look what happens here. So here, this is wait a minute. Okay, I think now I can speak again. So at this part, we have to think what this is. So this means that alpha I should be bigger than t, and also 1. So this should be, let's say, bigger than 0 or non-zero. It doesn't matter what we write here. So, well, it does matter, but bigger than 0 or non-zero is equivalent because it just takes the values 0 and 1. So that's this probability. And now we see that we can take sum I equals 1 to n, and now the integral. And, well, it suffices to take the integral up to alpha I, because if t is bigger than alpha I, then this probability is 0. And now if we take it up to alpha I, it also suffices to check just that the characteristic function is bigger than 0. Why is that? Well, if t is if t is less than alpha I, then this condition is trivially satisfied. So, well, that's exactly this condition. And so we again get the sum I equals 1 to n, and as before, this is the probability of AI. Then we get alpha I, probability of AI, what we wanted to get. And now there's one more step. So we assume y is an arbitrary integrable random variable which is non-negative. And now we know that there's a sequence of random variables converging pointwise to y, and these yn are elementary functions, so yn are of this form here. And you can prove this, or yeah, it's often proved in measure theory. Elementary functions. Okay, and now we want to apply the Beppo-Levi theorem or monotonous convergence theorem. So how can we do that? Well, these are definitely increasing the yn, so we can apply it for the yns, and then we get the limit of the expectation of the yns. Now we can apply part 2, and we get the integral from 0 to infinity p of yn bigger than t dt, and now we wanna interchange limit and integral. Now the question is, why can we do this? So let me at first write it down. So, well, we know certainly that so for n, if n gets bigger, then the yn get larger, and then also this probability, and so the integrand here is increasing, and so we can apply Beppo-Levi, and it's also yeah, well, that's already it, and we can apply Beppo-Levi, and so we have the limit here, and now I claim that this is the probability that y is bigger than t. And why is that? Well, let's write it in another way. So we have this limit, and we can also write this as a limit of an expectation of the set 1, or of the characteristic function of the set where yn is bigger than t. And now, as yn is increasing for n tending to infinity, also this characteristic function is, and so we again are allowed to take the limit n, and then yeah, well, the limit of this characteristic function is just the characteristic function of y bigger than t, and now we are done. This is the probability that y is bigger than t, and well, that explains this equality here, and so we are already done. Note that also there's a generalization to non-negative random variables, and then you have to consider something more, then you have to subtract something. And also there's a generalization to higher moments, so you can look that up if you are interested. So thanks for watching and bye.